scared me a little bit, but she has shown up. I think she's going to use the... Sure. Our next speaker is Pauline Winkler, and she's with Martin Marietta, right here in your area. And she's going to talk to us today about groundwater investigation and cleanup. Pauline, I have asked all of the speakers to take a few minutes prior to giving their talk to tell the students a little bit about themselves and a little bit of advice if the student is interested in being another Pauline Winkler. So Pauline, the floor is yours.
I'll stand up here. Can everybody hear me all right? Am I speaking loud enough in the back? No? Is there a speaker? How about if I move up here? Will that help? Can you hear me now? I don't have to stand behind the podium, so it doesn't bother me. Basically, I am Pauline Winkler, she said. I work for Martin Marietta. We operate a Paducah gaseous diffusion plant, which is owned by the U.S. Department of Energy. I have worked there for 14 years now. I graduated from Southern Illinois University at Carbondale, which is about 100 miles from here, maybe, something like that. I'm originally from Central Illinois. I'm a farm kid, so grew up with 4 brothers and no sisters. And like I said, I've been here for 14 years, and there's a lot of things that have happened over those years. I guess you'd say I've worked in civil engineering, I've done structural work, and probably for the last 7 or 8 years I have worked with groundwater investigations and putting in monitoring wells and that kinds of things. The talk I've got today is going to be very general. I'm not going to get into a lot of specifics. Those of you that like specifics, I'll be glad to talk with you later. It's a very, very broad topic. I'm not going to cover every technology that's out there or every field method that's out there. If there's something you've heard of that I don't cover, that doesn't mean it's not being used. The information that you have is probably correct. The kinds of investigation tools and things that we use are very, very site-specific. If you've got a different kind of site, you need to use a different type of tool. And I think you'll see that as I get into this presentation. Is there any questions at this point? Any more questions? Let me see if I turn this thing on. It might be good if the lights were turned down just a little bit, because I don't know how well these will show up otherwise. First thing here is the title page. That just gives me an idea everybody can see. Am I in anybody's way as far as seeing the overheads where I'm standing right here? Okay. That helps. First of all, every talk you do everything you do should have a purpose, and this is no exception. Basically, what we're going to do is, as I've mentioned earlier, provide an overview of groundwater investigation and cleanup, give you an idea of what it is, what we are doing, or why we're doing it, how it's done, and provide some results of investigation and cleanup activities. And that I'm going to do in a very general way. I'm not going to do that specific because your costs can vary a great deal by whatever it is you're doing, what kind of site that you have. The first question on here is, what is it? I guess the easiest way to explain that would be saying, all of us drink water in here, do we not? Basically, what we're doing is we're ensuring that the nation has safe groundwater. All of industry is doing some type of investigation and cleanup somewhere to ensure that everybody, when you guys get older, your kids will still have clean water. That's basically the goal of all of this type of work. Why investigations? Past industry practices have resulted in many areas having the potential to contaminate groundwater. That's not just government facilities, that's industry in general. And it was not done on purpose. It was things that were done 30 years ago that they didn't know would harm the environment. That's why we have changed the way we do things, like you recycle more now than you did back then. Number 2 is determine if any area where waste was buried or a chemical spilled is affecting the environment. Sometimes you spill something on the ground, it may not hurt anybody. If you have a large spill, depending on the type of area you're in, you may be harming someone, some fish, some animal, something like that. And that's basically the purpose, another purpose for doing this. Another reason is to select a method to control or clean up this groundwater or soil that's been affected. Why we have to have this information in order to determine that way, because like I said, everything is very, what we would call site specific. What kind of information is needed? There's 2 words I'm sure you're really going to love. I'm going to tuck this under the table, Pat, so I don't trip on it. Okay. One thing is detailed hydrogeologic data, and the other is analytical data. Now I'm going to explain what those are so you won't get totally throw somebody into the ceiling here. Have you ever dug a hole in the ground? You ever see the soil at the bottom of the hole and the top of the hole is different? Well, hydrogeologic data and geologic data basically is telling you what types of soil you have in that area. Some of you maybe have geology. Anybody in here had any kind of geology classes yet? Or earth science or something like that? Not seeing any hands. Okay. Basically, you're finding out, do you have sand down there? Do you have gravel? Do you have clay? That kind of thing. Where you get your water from, you find out whether it's gravel or if it's actually a sand. And that makes a difference on how well or what you have to use to clean up contaminated groundwater. This is a typical cross-section. What I mean by cross-section is you have, like this floor, that'd be soil underneath it. You take a slice through it and you look at the horizon and look at what it is. Here, these lines here basically show that we have a lot of clay up here, in these small areas here are what we call sand lenses. When you're drilling a well for your house, you can drill down and think, wow, I got some water here. And you may be in one of these little perched sand lenses, you may get water for 2 days and then dry up. Because you're not down in some area like this, which we call our regional gravel aquifer, which you can get many, many, many gallons of water out of. This thing ranges from anywhere from 10 to about 30, sometimes 40 feet thick at the plant where I work. And this is another formation below it that's got silts and clays and that kind of thing. All of this information is tied down to some geologic time periods and things that geologists use to map out which way groundwater is moving, whether it's moving down predominantly or if it's moving horizontally in one direction or another, east, west. This is another pretty picture. I don't know if it'll make a lot of sense to you, but it's 3-dimensional. It gives you an idea of how things can be a little bit different. You can see here, this is that regional gravel aquifer that I mentioned. There's some sand lenses, some clay, shows you the streams. If you've got a level surface up here, what you've got down below can be totally different. Now to explain in a nutshell what the analytical data is that I mentioned, basically get down there and you've got contaminated, you may or may not have contaminated groundwater. You've got to find out, or soil. You take samples, you send them either to a field laboratory or an off-site laboratory to find out what kind of materials are in there that may be, how can I say this, that are not natural to that particular environment. One particular thing that you see a lot of times in the groundwater is a thing called trichloroethylene, which is commonly called TCE. It's an industrial solvent that was used to clean metals and things by many, many industries, including the facility out here west of Paducah. And it gets into the groundwater. Sometimes it will even soak through clays. Another typical kind of contamination that you see is that from petroleum products. You see a lot of gas stations around, things like this. There's a lot of groundwater that's contaminated from them. However, they're much easier to clean up than something that's got this trichloroethylene in it. I won't get into a lot of details of why that is. You can do a whole day seminar on that particular problem. That analytical data tells us how much we've got at what locations. Okay, so how do we get this information? There's several different kinds of field methods. We do soil sampling, water sampling, we use geophysical methods, or a combination of all these three. And those, like I said, are very general, and I'm going to give them some specific titles of what those are. Like I said, this is not all inclusive. There's many, many more out there. Some investigation techniques are used, which is, this is very, very traditional, is using a hollow stem auger with split spoon samples, similar to what's used before they do building foundations and things like that. Or use the same thing with what's called a continuous sampler, and I'll explain what that is when I got some photographs. Hydraulic rotary drilling, dual wall reverse circulation, which is something we currently use at the DOE facility where I work. Rotosonic drilling is something that we're looking at right now to possibly implement. Hydropunch sampling, this allows us to get some samples of groundwater. Geophysical logging, that's kind of like black box technology in some ways. Cone penetrometer, geoprobe, install wells and piezometers, and believe me, everybody seems like they install wells and piezometers. We're trying to get away from a lot of this because this gives you a lot of waste. That's why we like to use some of these other methods here to keep from having as much waste from all these wells and things we've got out here. Plants begin to look like Swiss cheese. Aquifer testing. Aquifer testing basically gives us an idea of which way the groundwater moves. Does it move up, down, sideways? There's lots of different kinds of tests that can be used there. First photograph I have is some hollow stem auger drilling here. If you look over here on the side of this photo, you can see the little bit of piece of an auger. That's what's actually below the soil here. And these guys, as you see, they're in their personal protective equipment, PPE, that's required for that site. Many sites you do this as a precaution because you really don't know how contaminated it is. This particular site here is really not that contaminated, but this is a precaution in case they find something they don't expect. Next diagram here, this is a diagram of a hollow stem auger. And this is the last, what they call flight, the last section at the bottom of the hole. And if you can see, I don't know if you can see this very well or not. Can people see where I'm pointing? There's a hollow section right here by the bit to where you can take a split spoon down through here and you drive it ahead of the auger in order to get what we call relatively undisturbed samples, so you can actually see what kind of soil that you have down there and get an idea of what kind of contamination that you have. This is a shot of a split spoon. You can see what it is. It's split in half along this way, and it's got two steel collars here. Those collars are on that spoon. They drive it into the ground with the collars on. They take them off. They break out here, and then you've got a nice section. Looks like he's got some gravel and stuff here. What he's using there is a radiation meter to make sure that there's no rad contamination on that sample. They have to do all of this before they can send things to different labs off-site for control. Monitoring wells are another thing that's done. This is a typical monitoring well diagram. You see lots of these around. Basically, this is a stainless steel casing is what we use at the plant. PVC is acceptable, depends on what kind of contamination you have down there. If you have trichloroethylene at any high concentrations, it will eat your PVC, so you need to use stainless. At the bottom of this, there's a screen. They can be anywhere from 5 feet to 20 feet long, depends on your regulations and what you're looking for. This particular one here we're saying is about 10 feet. Believe me, this is not to scale. It can't be, otherwise it'd stretch the length of the room. You put a bentonite seal, which is basically some kind of mixture of high swelling clays, and then some more clay mixture and grout up through here. There's a pump in this well that leads up here to the top, where you can actually sample the water down here through the small pump using the packer. Now, if you've got a situation where you've got two aquifers, say you've got a water-bearing zone somewhere up here, but you want to sample the one down here, you have to put in what's called an isolation casing. This isolation casing, you put it into some type of clay material below this water-bearing surface up here, or water-bearing area, so you don't contaminate this groundwater with what may be contaminated up here in the process. I wanted to show you that because my next photo is going to show you what they're doing. What they're doing is actually installing an isolation casing. I didn't want to lose you totally. Basically what they're doing here is they're installing an isolation casing. You can see the guy's got his welding boot on. He's getting ready to weld these two pieces of pipe together. And then they'll install that. They'll install that into a clay layer, and then from there on they'll put a stainless steel casing down at a greater depth. This is another drilling method that we use, which is a dual wall reverse circulation. We've recently used this at the DOE facility where I work, and it's been great. It does not sacrifice the safety of the individuals involved or anything like that, but it has been much faster and much more cost-effective in getting us information. And that's one thing we're constantly looking for, is to minimize waste, not compromise safety, but decrease cost, because the cost of these investigations are enormous. We're talking the millions of dollars. This is an old photo of many years ago when I first started into this. This is actually a truck here that we've got geophysical logging equipment inside. It comes off into a boom, and we're taking it down into a well. It gives us an idea of what the integrity of that well is, and depending on the kinds of sources or whatever we put on the end of this thing here, geophysicists can determine what kind of materials we got out there, whether they're clays or silts, how much water may be there, if they are water bearing or not. We have some people at our plant that are very knowledgeable as far as that area is concerned. This is the inside of a cone penetrometer truck. This is a rod. It's another waste minimization type technology we've tried to use. It's actually pushed through the bed of this truck into the ground, as opposed to drilling and seeing all that waste you saw in the hollow stem augers. You don't see that with this. And you can also, it's got a lot of electrical type instruments at the tip of this cone penetrometer, which will give you a great deal of information on what's in the subsurface. And that information can be rather continuous. We're talking inches as opposed to every so many feet that you have to use in your split spoons. Okay, you've got all this information. Those are just a few. What are you going to do with that information? You've got to ask yourself some questions. First of all, now that I've got all this analytical lab information back, is the area contaminated? If it is, do you want to control or contain it? Do you want to clean it up? And the next question is basically just how clean is clean? I mean, that's the well over $1 million question in industry, and the regulators to this day do not have an answer to. Because right now, all of our technologies out there, very seldom or any of them that I know of, that will clean up groundwater 100%. This is the way one type of contaminant may move in a groundwater situation. This is basically trichloroethylene spilled at this point. You see it's passed through all these sand lenses. Instead of going out this direction, it's went through past the least resistance and flowed downward until it got to this, what I call the regional gravel aquifer. and has flowed on out this way. These different colors show you the different concentrations or different amounts in the groundwater. What's unique about some chemicals too, they actually change their composition will actually change sometimes. What you actually spill here, you may actually find byproducts down here instead of the actual original thing, which makes the problem a little bit more complex. Now these rods and stuff down here you see are not drinking water wells. Those are actually monitoring wells and things that were put in order to determine where this plume was going and that kind of thing. We've done a great deal to protect folks from getting any contamination in their drinking water wells or supplying water to those that do. If you had a different environment where you had bedrock closer, you'd have a whole different situation. Okay, you say, well, I've got something there. Here's some of the current technologies out there being used to clean up water. Now, this is not all of them. This is just a few. One is pump and treat. Another barrier walls, what's called a surfactant flush, which is basically a little bit from the oil industry. Horizontal wells are used, cap and covers, which you see on your landfills. I'll talk a little bit about pump and treat. I don't have any pictures because there's really nothing to see. Basically, well, there is if you want to see the treatment plant, I guess. You have a well in the ground, and you put a screen in it, and you pump the water out, and you pump it to the treatment facility, and then you either put it back down the well, or you carry it off somewhere else. It's perpetual technology. It's something that you've got. The big question is, if you're pumping and treating some area, when do you shut the pumps off? There's a lot of pump and treat methods out there being used, and to this day they're not sure. Some of the pumps they have shut off, and they found out that the contamination, they got like so many percent, which is, believe me, below 100% contamination removed. They turn the pump back on, turn it off, and that contamination amount will actually rise again. So that's what I prefer to call basically a control type technology more than actually a cleanup. This is a photo of a barrier wall that's being put in a site in Portsmouth, Ohio. It's a DOE facility up there. Basically, there's 4 drill strings here, and they are barrier walls can be put in different ways. This one in particular is what they call deep soil mixing. They're pumping bentonite through these lines here, bentonite slurry. It's about 30 feet deep, and they're mixing this bentonite with the soil to form an impermeable wall to contain the contaminant fluid that they're having. This is kind of a one-of-a-kind machine that you see here at Geocon, I believe, is the folks that were doing this particular project. This shot, if you can see it from the back, I don't know, there's paddles that you can see on here when you actually went to that thing. I went out to that site, it was quite impressive to see. I mentioned surfactant flush from the oil industry. There's not much to see on this particular photo, but what they're doing is they're taking what's called a surfactant, they're pumping it down into the well where they think they've got basically a source or a place where the trichloroethylene has spilled, and see if this surfactant will help loosen that TCE from the formation and come out easier. What we have a problem with many times, we've got contamination down there, but it gets trapped in all these little soil particles and attaches itself to the soil particles, so when you pump it, it doesn't actually come out. And the surfactant is supposed to help loosen those particles so you can do that. That's actually a research project that's been conducted at the DOE facility where I work. Many people call the landfills the dumps. Well, this is a schematic or diagram of the design of a landfill these days. Landfills these days are actually engineering design. They're not just a place you go throw drums or go throw your garbage. This below here is your existing subsurface here, your existing soil, and here is all these engineering layers that are put down before you ever install your waste here, and then there's another layer put on top of that. I can go into more detail on that with somebody later. I think our time may be getting close. Okay, cleanup results. I mentioned one time I would talk about cost on this, but I kind of backed off on that because your cost is so site-specific. We did some investigations out of the plant, and we're talking the millions of dollars depending on how big the site is that you're looking at. The result of all the cleanup efforts from the conventions and things that I have attended is basically there's a lot of work out there to be accomplished. We're not anywhere near where we need to be. There's a lot of methods, but there's no ideal solution. As I said, there's nothing out there we found yet that's going to clean up trichloroethylene 100%. There's always some residual in the ground. One real key thing that I want you to take home, there's a different solution for each site. What may work somewhere in Paducah may not work a couple miles down the road from Paducah. It depends on what kind of sites you have. It needs to be investigated. Nothing to date, as I said, will clean up the groundwater to 100%. What we need now is we need better research and minds. That's where you folks come in. That's a challenge for the future, folks, is to clean up our groundwater. We need more people that can understand this situation and to work with it. A lot of this stuff was done 30 years ago. Our parents did not know what the impacts would be. Now we know some more what those impacts. We're trying to clean it up, but we're trying to come up with new things every day. The last thing is we need more bang for the buck. We're spending a lot of money, but it doesn't seem like we're getting a long ways. It's estimated about $750 billion to $1 trillion will be spent on groundwater investigation in the next 30 years. And right now there's over 36,000 contaminated EPA sites. And there's probably more between now and then. Is there any questions or any comments? Yes.
What is TCE used for in Marbury? Is it a greaser?
Yes. So it's a solvent that's used to clean metals. There's a lot of uses for TCE.
And so what they did 30 years ago was that they just buried the TCE?
Oh, not necessarily. We're still investigating to see exactly where that TCE is coming from. The TCE was used in a lot of different places around the facility, and at this point in time, we really do not know. They know some of the sources. I don't know specifically what those sources are. There's several areas that are suspected right now.
Have you all ever thought about using bioremediation?
Oh yes, we've been looking at that. Bioremediation is something that you have to have an environment where the bugs can live, and that's something that's one of the drawbacks we have found with bioremediation. Anything else?